So, welcome to everyone. So, we are here for the fourth seminar in the series of the Principal Investigator series, stories that we organized here at the University of Trento to learn from expert people and in different fields how they succeeded in achieving their career results and in acquiring interesting projects. Today, here in this series, we have Sara Bernardini. She started the PhD directly here in Trento a few years ago, and since then she worked in very interesting projects. She collaborated, for instance, with NASA during her career, and then she moved to the UK, where she's still now, and currently she's a full professor in artificial intelligence at I don't remember exactly your
Royal Holloway University.
Royal Holloway University of London. Sorry for this. And today she will introduce us to AI and robotics for extreme environment, where she will describe two interesting projects. What are the challenges behind this project, and how she managed to achieve to get this project funded, and she will tell us a bit about her story. So, Sara, you are on the stage.
So I'm going to share my screen. Can you see the screen?
Yes.
Great. Okay. So thank you so much for the presentation. So actually, I want to thank Professor Rovery for inviting me to give this talk. As he said, I was a student of the doctoral school in ICT in the past, and actually the ICT school provided me with great opportunities to foster my career. As he said, I was able to do an internship at NASA Ames Research Center in California during my PhD program, and also then I got a contract there so I could stay longer, and so I am very grateful to the school. So it was a really great period for me, so I'm very happy to be here to present my research, to share it with you. And so clearly, because the talk has a limited amount of time, I will try to present as much as possible, but if you want to learn more, this is my website here, so you are welcome to visit it, and I would be very happy to interact with you if you have other questions, you want to contribute in any way. So my research is about AI and robotics for extreme environments. And in particular, all my projects are about generating autonomous and intelligent behavior for robotic systems. And as you might already know, autonomy refers to the system's ability to organize its behavior to accomplish goals. And when we talk about shared autonomy, we refer to agents that are autonomous, but they share their autonomy with humans. And this is a very rich field of investigation in which three dimensions matter. The first is whether the robot and the human share the same physical space or not. The second is what is the role played by the human in this shared autonomy interaction. And the third one is whether the human and the robot can communicate smoothly with one another. And now I'm going to explore the interplay between these dimensions in the context of extreme environments, which are at the core of my research. So extreme environments are all those environments that present very challenging and extreme conditions that make it difficult or impossible for humans to work in those environments. So examples are space mission operations or operations in nuclear facilities, subsea operations, and then applications in mines, underground, oil and gas, and so on and so forth. So in all this context, usually what we want to try to do is to send robots instead of humans as much as possible. So in this case, if we consider this spatial dimension of interaction, we see that the human and the robot usually don't share the same physical space. And then this is the whole point, right? Is that we want the human to remain safe and then to send the robot in the remote space in order to perform tasks. So they don't inhabit the same physical space. Now, due to this, in many cases, there are some significant delays in communication between the robot and the human. Imagine, for example, space mission operations or operation underwater. In this case, there is such a delay in communications that it is impossible to teleoperate the robot or to control the robot closely. And then finally, if we consider the role of the human and the robot, usually what we have in application in extreme environments is that the robot is the actor, so-called the actor, because he's going to do the actual activities to perform the tasks, and the human is usually far away and is there to try to observe what the robot is doing and supervise the mission at a distance. Now, notice that usually the same human operator can, supervise several robots. And so we say that the robot is the actor and the human is the observer in this kind of applications. Now, clearly each extreme environment has its own specificities, but we can see that in fact they share several common challenges. And here I will highlight the most important ones from our point of view. So the first one is that the robots need to exhibits a high level of autonomy. And this is because those robots usually functions beyond line of sight. So they need to be independent and they need to be able to do tasks, and they cannot rely on direct help from the humans if something goes wrong, because the human is far away. Then clearly robustness of operation is crucial here. And this is because these are critical environments where any mistakes can lead to fatal consequences. So we need our robots to be exhibiting an extremely robust behavior. And then also in these extreme environments, there are safety standards that are very strict in place. So those standards need also to be satisfied by the robots. So safeness of operation is crucial, and also the ability to provide guarantees on performances for the robot. And then also imagine that these environments are characterized by a high level of uncertainty, and so the robots needs to exhibit a flexible behavior, so dealing with all these uncertain factors, and also flexible because in these environments many tasks need to be performed. So we cannot really train the robot to do exactly one thing like with machine learning techniques. We need to have a robot that can perform a variety of tasks with sufficient robustness. And finally, in extreme environments, there is always a human who is in charge of supervising the mission and who is responsible for the mission. I mean, a human or a team of humans. So in this kind of environments, it is very important that we established a relationship of trust trust between the human and the robots. And the human needs to be able to understand what the robot is doing at all time and needs to be on board with all the decisions of the robot. And so it needs to trust the robot to do the right thing at the right time. So let's see how we actually tackle these challenges. So in all these systems that we are using in extreme environments, we always combine the perception and the mobility layers of the robots with a deliberation layer. And this layer is based on AI planning. So some of you might be already familiar with this, but in any case, AI planning is an AI technique through which the robot can answer the question, how should I act? And the idea is that whenever we have a task that is complex, and so it requires some thinking, some deliberation, the planner is there to select and organize actions for the robot to bring about a desired outcome. And we use planning at different levels. So we have mission planning, which is going to create a plan for the entire mission. Then we have task planning that takes care of the various activities that the robots need to perform. And then we have motion planning that is closer to the hardware and so has to do with finding a path for the robot, or has to do with controlling the joints of the robots. And so we use planning at different level of granularity. Now, as you might already know, AI planning is a model-based techniques, which means that we use a causal model of the world and of how the actions can change the environment to reach a goal. And I use different techniques in AI planning, from PDDL planning, which I will discuss here later, to probabilistic planning, to reinforcement learning, and so on and so forth. So now I will go a bit more into the detail of my projects in extreme environments. So currently I am the co-principal investigator of 3 projects in this space of extreme environments. And these 3 projects, MIMRee, Prometheus, and Connect are, they are all projects funded by industry and by the UK Innovation Agency, which is called Innovate UK. And here I participate as an academic to provide the innovation part. So the more like cutting edge techniques that these companies needs to use to do these applications. And so I will describe this briefly, but as I said, these are the websites also of the different projects, so you are welcome to have a look at them. And as I said, I would be happy to interact with you about any of those projects. So let's start with the first one, which is called Prometheus. So Prometheus is about exploring mines that are close to the network rail. And in fact, currently these mines are explored by human operators, as you can see here, but these are extremely dangerous tasks. And there might be fire, there might be gases in these mines. So these are extremely dangerous environments. And so it would be much better to avoid sending humans in these spaces. So our idea here in our consortium is to develop a drone that is reconfigurable. And this drone will be able to inspect these mines underground by using AI techniques and also advanced sensing techniques. As you can see, the drone is quite small and can enter into places, holes that are 150 millimeters. And then once it reaches down, it will open up, the drone opens up to be able to fly inside, beyond line of sight. So as you can see now, the drone is open here like a flower, right? And is going to map the area. And this is what I am responsible for. This intelligent exploration of the mines to create a volumetric map and a map of the environment. Now, I want to tell you a bit more about these intelligent exploration techniques that we use. As you can see, close to the title, I put some publications that my team and I have done on this project. So this one was, for example, was presented in IROS last year. Here in Prometheus, we have a navigation layer, which is based on using rapidly exploring random trees. And our navigation system is guided by a high-level reasoner, which in turn is informed by an exploration module. Now, our intelligent exploration framework makes smart decisions by combining perception, navigation, and knowledge engineering using a broad range of reasoning processes. So to tell you a bit more in depth about this, as I said, our navigation system is guided by a high-level reasoner, which takes in consideration this semantic network that you can see here that the robot constructs while it's exploring the environment. Now, this semantic network, I am sorry because my mouse here doesn't work. I don't know why, but in any case, in this case, you can see that we have three regions, region 1, 2, and 3, that are represented here in this semantic network. And then the robot's knowledge is represented in terms of environmental features, hazards, and exploration information. So in this case, for example, we have that region 2 has some fog in it. See, this is on the right-hand side of the screen and is not yet explored, while region 3, for example, is clear and also is not yet explored. So now our high-level reason about this map to decide that, for example, if we have some time constraints here, we prefer to go to region 3 because it's clear, so we will be able to gain more information by using our time exploring region 3 instead of region 2. So our high-level reasoner actually uses logic-based reasoning over the semantic network to evaluate candidate regions and to decide the best region to explore next. So here you have a set of first-order logic formulas that guides the exploration. So in this little example that I put in this slide, you see on the left-hand side of the screen, we have Phi1 that's a formula that finds the next feasible regions. And then we have Phi2 on the right-hand side that finds the best feasible region to explore next. So you can see that it is notable here that we are using first-order logic to guide the exploration. Because this makes our approach transparent to the human operator in the loop and also fully verifiable. Now, we are working, okay, so these are actually some results and that shows that our approach that is represented here is able, thanks to this exploitation of semantic information, to explore bigger regions in a shorter amount of time. And so our evaluation confirms our claim that exploration can leverage semantics to reason about the best way to map an environment. Now we are working on an improved version of our autonomy architecture for exploration. And so what we have done, we have improved the rapidly exploring random trees in a way that we call risk averse, because in extreme environments, usually, and in particular in these applications about mining, it is very important to be able to retrieve the robot at the end of the mission. So we want the robot to be able to go back home and come out from the mine. And so in this risk-averse version of RT, what we do is we allow the robot to reason about known space in order to find paths, instead of also considering unknown space, because when he wants to go back home, the robot needs to be able to take a safe path. So we have modified this technique to make it more risk averse. Then we are using now, instead of the semantic network, what we call the double weighted reachability graph. This is a graph that we have developed, and this graph represents the structure of the environment, also keeps in memory dead ends and places already visited, so that we can maximize the space explored in the time that we have. And so also we keep track of the best candidates that needs to explore next. Now, to actually choose the next, the next point to explore, so to choose between the different candidates that we have in the open frontiers of nodes that we still need to visit, what we do is we use a utility function, which is based on information gain, but also on safety constraints, because again, in this application, safety is very important, and also on a plan length, because we also want to consider the resources that the robot has. Because as you know, flight time is limited. So this is our improved architecture. And in fact, here you can see that we have used to map real world mines, actually in the UK. Here in the video, you see a mine that is Nail Beach in the UK, but also in the other picture, you see that we are able to map and to create a volumetric map of quite sophisticated mines. And so these are all real world experiments here. And then after we have the map, we are able to bring back the robot home by following a safe path that is going to be also very efficient. So you can see here now the robot is going back home directly. Okay. So now this was my first project, Prometheus, so about mining. Now let's go to see another one, which is called MIMRee. So MIMRee, in this project, our ambition by the end of the project is to have the world's first fully autonomous platform for the inspection, maintenance and repair of offshore wind farms. So this video here explains the mission. Okay, this one actually. So in this case, we have that we have an AI control system onshore, which plans and launches a mission. Then, as you can see here, we have an autonomous boat that goes from the shore to the actual wind turbines, and this scans the turbine at a distance. And this is very good because we don't actually need to stop the turbine doing that. Then we have drones that can be launched by from the boat that are going to scan and map the blade's surface of the turbine. And then if the drone decides that the blade needs repairing, the drone can pick up a maintenance robot that you can see here, which is a climbing robot that has the capability of walking over the blade here and to go to the place that needs repairing, and then the drones come back, pick up the robot and bring it back to the autonomous boat, and then at this point the boat can go back to shore. Here you here you can see a gazebo simulation of the same mission. So in all this project we use simulation quite a lot because, as you can imagine, it is extremely expensive to deploy these robots in real trials. So first we create sophisticated simulations of our missions to make sure everything works well, and then when we deploy in the real world. And in particular, we use gazebo quite a lot. Now, let me show you the system a bit more in depth. As I said, we have an onshore AI-based control center here that you can see at the top part on the left. And in fact, this is the core of my responsibility to create this AI-based control center. And this control center is going to create plans, again, at the mission, task, and motion level for all those robotic assets that you can see in this slide. So again, we have this autonomous surface vessel that is actually provided by the company Thales. Then we have a set of UAVs or drones for this project that has the goal of scanning the blades and also transporting this inspection and maintenance robot that you can see at the bottom part on the left. And as you can see, this robot has 6 legs and is able to walk over the blade. And each of the feet of the robot has some electronic skin. And this has 2 purposes. The first is to stay attached to the blade, and the second is actually to be able to feel the surface of the blade to understand whether the blade needs some repairing or maintenance. And then attached to the belly of this robot, we have this multifunctional arm that you can see at the center of the slide. And then this multifunctional arm has some end effectors that are capable of performing some repairing tasks on the blade. It could be, for example, scraping to remove something wrong on the surface and then spraying back some material, and so on and so forth. And finally, we have a pretty sophisticated a system to actually transport this maintenance robot and deploy it on top of the blade and then pick it up and put it back on the boat. Imagine that this operation in which robots comes to physical contact, those operations are very difficult to be performed precisely and without risk. So this is a quite challenging part of our system. And also just to mention that the autonomous boat has also on board a camera that is capable of scanning the turbine at a distance. So as I said, we avoid the downtime of shutting down the system as much as possible, because clearly whenever the turbines are off, the companies clearly lose the ability to produce energy. So this, as you can see, is a pretty sophisticated multi-agent system. So constructing a complete mission plan in our project MIMRee require addressing multiple issues: communication, coordination, cooperation, of course, between the multiple assets, but also task and path planning and replanning. Then we have a human-machine interface so that a human operator can interact with the system, and domain representation for our planning. So what technology are we using here? So this on the left-hand side, you see actually our architecture for autonomy. And the idea here is that we use ROS, the Robotic Operating System, as the backbone of our architecture. And then we use, again, planning to create the mission and task plans. So the mission plan will be a plan that has to do with, for example, it could be a long-term plan that could be for even weeks or months, and will be about inspecting several turbines. And then the task planning has to do with the tasks that each robotic asset needs to perform. And we use, in this case, PDDL planning. So you might be already familiar with it. PDDL stands for a Problem Domain Definition Language. So it's a logic-based language that allows us to describe the world in which the robot operates, and also the actions that the robot can perform to change the environment. So in this case, for example, for the drone, it will be scan the blade or pick up the repairing robot, and so on and so forth. And then we use off-the-shelf planners, POPF, for example, to actually solve the planning problem and create plans. And we have clearly a way to translate the plans at the high level to ROS commands. Now, the innovative part of our work here is this problem generator box that you can see at the bottom with the discrepancy checker and model learner. Now, the idea here is that in this kind of missions, time is really critical, because imagine that the companies wants to use robots to be more efficient. So anytime we fail with our plans, we have to replan, we are wasting time. We are wasting the time of the robots. We are also wasting time because the turbine at that point will be shut off, and so we are not generating any energy. So it is very important in this kind of domain that we avoid replanning as much as possible. So what we do whenever we perform a mission, we try to learn from what went wrong in the previous mission. So we have this model learner that continuously improve the model, the PDDL model that we are using based on previous failures, and also based on the behavior of the human operator, who sometimes wants to take control of the robots. And so we try to learn which actions performed by the robot the human operator didn't like. The operator probably didn't judge these actions useful. And so we try to avoid those actions in the future. And also, for example, we managed to be able to learn the duration of the actions quite accurately, because based on previous failures, previous times in which we were not capable of performing an actions in the required time window, we learn for improving our domain. And so if you look at these graphs on the left, you can see that by using this problem generator, in which we have this learning of some models parameters, we are able to avoid replanning in several circumstances. And so this was quite successful. Now, we also have developed a pretty sophisticated interface here for our system. So in this bottom part here, you see a GUI in which the human operator can decide which turbines we need to inspect, and also he can decide if the operator wants only inspection, also maintenance, repair. So in this visual GUI here, it can just set up the high-level goal of the missions. And then here we have a digital twin. As you can see, I'm going a bit faster, but here is like the operator is on board of the boat and is actually going very close to the turbine that the robot is inspecting. And so you can see the boat here, and then you can go very close, and then for example, here it starts raining, and so on and so forth. So we have a quite, sophisticated architecture here. Here we have a webcam. So we try really to make it very easy for the human operator to feel that he or she is in control of the mission. And this was, in fact, developed together with the company Thales. So this is for MIMRee. And now I will go to discuss the last project I wanted to cover today. This is called Connect R. As you can see, we have these two papers at ICAPS coming up in August. The conference will be. And okay, so in Connect R, we started from the observation that in many situations in extreme environments, we actually have problems in heavy ground robots traversing the environment. And this is because there might be water, there might be sludge, there might be obstacles, and so it is difficult for the ground robots to go from one point to another point where something needs to be done. So our research question was whether it was possible to create a structure structure that self-assemble itself in an structured environment so that it can provide structure for another robot then to come in and go to a specific place to perform tasks. And we have explored this research question in the context of nuclear decommissioning tasks with the company Bernardini. And so in particular, Connect R focuses on nuclear decommissioning tasks, but it can be used also in other contexts. So as I said, the goal is to develop a multi-robot system which self-assembles itself into a stable structure in a target environment with different goals. The first one is to offer structural support to an environment that is structurally unsound, to create a physical structure which different robots can traverse to perform useful tasks in the target area, and to provide a uniform environment that reduces the reliance on path planning and state estimation in environments that are inherently uncertain. And here I just provide you with an example. So in this case, we have that these building blocks, we will see that those are the building blocks, these four these cuboids with 4 spaces, and they self-assemble itself into a cube in this case. And then we have this little bot that, as you can see, works in this way, that can traverse this structure to reach any point here where some jobs needs to be done. And so, as I said, this is going to be used in nuclear decommissioning tasks, because in these cases you have rooms that human beings cannot enter. So our goal is to send this little bot to do the tasks, because the bot will have an end effector attached to it that could be a gripper, could be a hand, or whatever we need. And then in order for the bot to reach the point that needs maintenance or needs to be clean or things like that, we will develop a structure that the bot can traverse. Now, let's see how we do that. So our first task is to understand how do we create this multi-robot system that self-assemble itself. Now, we came out with these building blocks that you can see here on the picture. These are cuboid with 4 equally spaced connection points that you see in light blue here on each face. And then at the end of each cuboid, you can see there are 2 actuating manipulators. And these have 3 degrees of freedom, as you can see here in the bottom part of the picture, so they can rotate in 3 different directions, and these are really the driving force of the robotic structure, as we will see in a moment, because it is thanks to the movement of this manipulator that we can create the self-building of the structure. Then also we have a basic locomotive ability here. As you can see on the right part, the cuboid can extend in this horizontal direction. And then it is important to note that each unit gets power and structural support by being connected to other units. So for the structure to be live, all the cuboids need to be connected with one another. And then we have an initial structural robot that receives powers, and then the power gets traverse the structure from one structural robot to the other. Now, we have found that we need some primitive actions in order to create structures. Imagine that here we have to consider spatial constraints for the structure to be able to build itself, of course, but also structural robustness constraints, because we want a structure that is safe, okay? We don't want the structure to collapse when the robot traverses it, otherwise we defeat the purpose of the system. So we had to come out with some primitive actions that allow us to build sophisticated structures, but also to satisfy these constraints. And so here you can see one action that is traverse, that is just one cell displacement over a unit above another unit, as you can see here. Then we have a place line, which is to create a vertical line. And in this little video, you can see that are the manipulators that create the movement of the structure. Then we have, for example, vertical traverse that is to expand in the Z direction. And then we have, for example, this one is to create a right angle. So in the end, we found out that we need these 7 primitive actions in order to create structures that could be quite flexible in their final configuration. And also, all these actions can be described in terms of their initial and final configuration. Okay, now that we have these primitive actions, how do we go about constructing the final configuration? Here I just put an example to show you that with these 7 actions, you can develop quite sophisticated structure. So this one has been done fully automatically, so with no human intervention, and it is the system that decides how every cuboid needs to move in order to create, in this case, a cube. Okay, so as I said, this is done with these 7 basic actions, but now we have to see how we have done this automatically, not by hand. And this is clearly, we don't want to do it by hand because we are dealing with quite complex operations. Imagine that just to create this structure here on the right with just 4 robots, we had to use 10 actions. So we really want to avoid to write scripts to create a difficult final structure. And also we want to have some flexibility, right, to be able to specify any final configuration and be able to achieve it automatically. And again, as I said in the beginning, it is very important, especially in nuclear decommissioning tasks, that whatever the robot does, it comes across as clear to the human in the loop. So whatever we do needs to be explainable, and the human in the loops need to trust the behavior of the robot, because these are critical environments in which really the human operator cannot allow mistakes. And also in this kind of environment, because they are usually unknown before we go into them, we lack training data, and so we cannot use machine learning techniques. So here AI planning again becomes a natural choice because it satisfies all these constraints. The problem here is that if you have been dealing with AI planning is notoriously difficult in 3D spaces, and we are here in 3D spaces. And it is difficult because there is a lot of symmetry you have to deal with, and your state space explodes, becomes very big quite easily. So we had to come out with a smart representation of our problem in PDDL. So again, we use PDDL, but before getting there, we had to really think about how to find a succinct and efficient representation for this problem in order to create plans quickly and in an efficient way. So by studying this problem and trying out many different representation, we came out with this one that, as I said, we are going to present to ICAPS very shortly. And the idea is that all the connections point of the robotic units that you have seen, the light blue points in the cuboids, become the points in a 3D map. And then, so we have this 3D map constituted by those points. And then each unit, each robotic unit can be represented only by using one point, XYZ, that is the starting point, and an orientation. We don't need to represent all the 4 points. And finally, we notice that actually the robotic units are functionally identical to one another. So we don't need to represent each robotic unit specifically. What you need to do is to know how many you have available to develop your structure. And whenever you use one, how many are still available. And so we use a countable robot representation in which basically, we know how many robots structural units we have outside the environment, and whenever we introduce one, we subtract from this number. And then we have this predetermined entry point for all robotic units. So now, thanks to this representation, we were able to create a PDDL model that is quite useful. In fact, in this model, we have that the objects represent the positions on the axis, so they are basically the coordinates. And then we have 9 predicates really in the representation. And here I put just some of them, the most important. For example, the first one is at unit XYZ angle, and which means that there is a unit, a robotic unit, with origin in XYZ and orientation angle. Then we have, for example, stat at XYZ that represent the fact that in point XYZ, this point is occupied. Dynamic at means that the point XYZ is occupied by a structural robot, which means that now it's occupied but could be free later, and so on and so forth. Then we have actions that correspond to the 7 primitive actions that I show you in the beginning. And so in the end, we have 20 actions that are variations of those 7 that you have already seen. Now, if you are familiar with PDDL, I just put here a description of one action, this simple action of traversing. And you can see that the description is fairly sophisticated here. Now, for the plans, for example, in this case, for the cube I showed you before, in fact, we had to use 17 structural robots, and in our plan, there are 86 actions. So I would say that the domain in this case is quite complex. Now, and I put here these slides. I don't want to go into the detail of it, but just to say that
Sara,
yes?
just a quick question. So were ground actions or?
So no, this is specified at the lifted level, and then we ground the domain because we use.
So the actions, the real actions are way more. So those are just the
so those are the PDDL actions, and then
okay.
we ground the domain later. Yes, when we do planning. Yeah.
Okay. Just curiosity.
No, absolutely. And then, so here you can see the coverage in the first line, and we are comparing our representation with some naive representation that could be used to deal with 3D spaces. And unfortunately, my mouse, I don't know why it's not working, but on the right-hand side here, you can see that only by using our canonical representation in reddish and pinkish, here we are able to keep solving problems even for big spaces and with a lot of structural robot, like 15 structural robot and grids of 15 by 15 by 15. And so also we were able to solve some of the problem optimally, again, with our canonical representation, whether this was not possible by using, a more naive representation. Okay, then also for this project, what we have done is to develop a GUI for the human operators, because clearly we cannot expect the human operator to understand the PDDL or anything like that. So the human operator will have the opportunity to create the environment here visually, and then to specify the entry point and the exit point. I mean, the point we want to reach inside the space. And then once he has done with this configuration by using this GUI, we auto-generate the PDDL description, and then we solve the problem by calling a planner, and then we load the plan, here you can see at the bottom, and we simulate the plan, as you can see here in this simulation. In this case, for example, you see that we want to reach this green point on the other side of the wall, so we have to create a bridge here. So after we finish with this, we have a bridge, and then the little bot I showed you before can traverse this bridge to reach the green point in which things needs to be done. And also the bot is, the behavior of the bot is underpinned by planning, but unfortunately I don't have much time to discuss this here, but we use some planning system also for the bot. So both the construction of the robotic structure and the bot are underpinned by planning. Okay, so this comes to the end of my talk. At this point, I just want to leave you with some open problems that we see still in extreme environments. So the first one concerns robustness of operation. So as I said before, robustness of operation is critical in extreme environments, because these are are environments in which making mistakes is extremely costly. So we need to be able to reason under uncertainty, because there is a lot of uncertainty, a lot of unknowns in these spaces. And so we want to be able to reason about uncertainty and risk online to achieve safety. Then the other point I was making before is that we need to ensure transparent and trustworthy human-robot interaction. And this gives rise to many interesting research questions that, in fact, I am tackling in also other theoretical parts of my research. For example, we want to create a behavior for the robot that is understandable to the human operator in the loop. So the human is going to look at what the robot is doing, and hopefully the human will be able to understand very easily what are the goals of the robot, what the robot is trying to do, without asking any explanation. So we need to plan not only for efficiency, but also for transparency. But if the human wants to ask a question about the behavior of the robot needs to be able to generate concise and compelling explanations for the human in the loop. And finally, the last point is about acceptability of autonomous robots in extreme environments. And this is because, of course, there is still some skepticism in the use of robots in these environments, because, as I said, these are critical situations. And also we learn by working with the human operators that some of them really enjoy the danger part of their work. And so our idea here is really not to replace human operators, but simply to offer support and to create a team in which we will have both the humans and the robots trying to cooperate to achieve a final goal. And so this concludes my talk. I just want to thank my team at Royal Holloway, and then also my sponsors, so Innovate UK, and also all these companies that you can see here at the bottom left, and my other academic collaborators. As I said before, I am open to questions even after the talk, and even if you want to collaborate somehow, if your research is linked to this, I would would be very happy to interact with you about any of this if you are interested in producing autonomous and intelligent behavior in challenging situations. So thank you so much for your attention, and thank you for participating.
Thanks, Sara, for this nice talk and this experience. So, are there questions from the audience? I mean, you can either write it on the chat or say, switch on the microphone and ask. Okay, let me first, ask one thing. So I've seen that you were using PDDL planners that leverage also on temporal constraints. Mm-hmm. If I understood correctly from your presentation, because POPF deals with that. So. When my experience with planners like POPF and others is that unless you introduce very sophisticated heuristics, or you tune properly the model, or unless you tune the heuristics, they do not scale to realistic problems. Mm-hmm. That is my experience. So were you facing the same problem, or they say
yeah, of course, that's always an issue. So for the MIMRee project, the one about offshore wind farms, in that we use temporal planning, in fact. And yes, we had to both tune the model and also to work on the heuristic. So we we don't use any domain-dependent heuristic. We try to avoid that. But we came out with a way in which we use also external solvers to do some of the calculations involving probabilities and things like that. And so we came out with strategies through which the system can analyze the domain and try to automatically come up with some improvements of the heuristics that are provided by the basic planner. And for the connect-R, in fact, thanks to this canonical representation, because in connect-R, the one about the structures, mm-hmm. we don't use temporal planning. Okay. Because in this case, time is not crucial, really. In nuclear facilities, safety is more important than being fast. So we use fast downward. And in that, the challenge was to come up with the efficient representation. So it was more about tuning the domain, finding the right representation for the domain, because as I put in my slide here, you can see we say translation error and search error. In many cases, you see, we didn't manage to even to solve the problem, or even to translate the problem, because as you know, fast download translate from PDDL to FDR, and so we couldn't even, start planning. So basically, coming up with a good representation of the problem was key in order to solve big instances like those in this part.
Another comment. So in the project I was involved with, so we were, or say it was in the pipeline planning for deploying pipes under the sea. We tried to experiment with PDDL planner, but we faced the two main problems. One is a representation problem, because it was not easy to encode the kind of goal that we were interested in. Mm-hmm. And second, assuming that we find some solution for that, so the problems were so huge that no planners were able to deal with that. And what we end up is to create a sort of an ad hoc specialized planner with domain-dependent heuristic to have it work in the real domain. So I'm really happy that you managed to at least use an an off-the-shelf plan
I
to
mean,
some extent.
yes, it was a lot of work to do the representation part. Also, we had to. I mean, I always also say to the students, right, that usually my advice is to not to always go for the same technique, but try to explore different techniques. So we had to really find the right planning techniques in each of these applications, and so some of them PDDL made sense, but in other didn't. For example, for the drone, really that is more like path planning. So we use more like other techniques, like I said, rapidly exploring random trees. We don't use PDDL, but when we use PDDL, it was so it took a long time to come up with the right representation. We had to try so many different things, but also, as you know, sometimes you come up with a representation, but then no planner managed to actually be able to handle that, and so you have to start again. And so I would say that the representation part is always key, and also working on the heuristics. Also, in some cases, we had to resort to external solvers because, as you know, the metric side of planners is not the most developed, but these external planner solvers proved quite useful to solve some of the problems. So it's a lot of work. I mean, nothing really works on the shelf, but at least I think this proves the potential of planning, that we can deal with real world problems if you understand the problem very well and if you spend a lot of time in,
doing.
Yeah.
And so are there questions from the audience?
One.
Yeah.
Hi, Luigi.
Ciao. So my curiosity is that there is a lot of ongoing work on joint approaches where task planning and motion planning is considered jointly, because this opens up for important optimization opportunities that would otherwise be inaccessible if you think of the two problems separately. Do you think that a joint task and motion planner could make sense for this type of applications?
Yeah, no, you're absolutely right. So for the first project I presented, Prometheus, in fact, our next step would be to create a joint approach for task and motion planning, because now we have dealt more with motion planning only, but then we also have other tasks. We could have other tasks, like, for example, collecting rocks inside the mine, or, so at this level, it's just exploration. I mean, but I think the next steps would be also to combine exploration with some, kind of tasks like collect this rock, or I don't know, we will have also other drones collaborating. So at that point, we believe that we need more an integrated approach to do both together. For Connect-R, well, I think for now we have dealt mostly with the construction of the structures and with the boat reaching the whatever point we need to do things. But again, then the bot will have a final end effector that we'll have to use, which will be a manipulator. And so in that case, also in manipulation tasks, usually it makes a lot of sense to do task and motion planning together. And also for the MIMRee project, we haven't got there, but I think it would make sense there as well. Imagine that these projects are quite, they are really a full immersion, because Innovate UK, this agency, wants us to deliver in 2 years. So sometimes we have to focus on one aspect first, and then we keep going, building on the projects, and keeping going with the research side. So I think our next step would be, in fact, to try to have integrated task and motion planning.
Indeed, I agree that it's a very interesting topic. Other questions? I have another curiosity. So you were mentioning ROS plan and the ROS infrastructure. Yeah. Were you using the ROS 1 or ROS 2?
So we use both of them in different projects.
Okay.
Yeah. I mean, ROS is a bit painful because it keeps changing, so you have to also change your modules a lot, I would say. But it's a great architecture. I mean, I use ROS across all my projects, but still, also that is a lot of work.
Yeah. Well, just a curiosity.
Yeah.
Okay. Other questions? Okay, so if there are no other questions, so let me thank again Sara for her presentation and giving her insight on these interesting projects. And if whoever is interested can send me an email and or Sara, and I will forward the slides. So, I mean, Sara, if you can send the slides to me, it's not a problem. Then I will take care of circulating them to whoever want to see more details then.
Yeah, thank you so much for the invitation. I really enjoyed it.
And yeah, it was the same also for us. So thanks again to everyone.
Bye.
Bye.
Have a good day. Bye. Thanks.